Hi, welcome back to Chemical Engineering Statistics. This time I will discuss about the concept of sampling distributions, which is the theoretical basis for the inferential statistics next week. I introduce the concept of sampling distribution in the following simple example. Suppose we conduct a survey of the amount of household electricity consumption in the city of Bandung. Then we can define the target populations as all the families of Bandung citizens. Because it will be far too expensive to carry out a census, it was decided to do a sampling, where one sample was determined to contain 10 families from each kelurahan. Then we calculate the average electricity consumption per family for each of the samples. Remember, one sample consists of 10 families. The image below illustrates the process of taking data and calculating the sample mean. So, with the existence of a total of 151 kelurahan in Bandung City, our survey will collect 155 sample mean values. Recall that we can express any measurement data as a frequency distributions. Likewise, with the 151 mean value of the sample. The frequency distribution obtained from the set of sample means is called the mean sampling distributions or sampling distributions of the mean. We can perform a similar procedure for any sample identifier quantity, for example, the sample distribution variance, sample distribution standard deviations, and so on. This image is an illustration of the concept of preparing the sample distributions, in this case, the distribution of the sample mean. From the population, we take a number of samples, usually with a constant sample size. So for our previous example, the sample size was 10, and our number of samples was 151. Then we calculate the mean for each sample, and the set of the mean values of the sample can be stated as the frequency distributions. This is, the blue one, is the distribution of the sample mean. Please pay attention, as with any frequency distributions, we can find the identifier of the sampling distributions. We have one of the most important theorems in statistics, the central limit theorem. Please have a look at the distribution of the arbitrary populations as shown on the left. From this population, we take a fairly large number of samples with a constant sample size of n. Remember, you have to distinguish between sample size and the number of sample. Okay? The mean value of the sample is then arranged into the distributions on the right. So, what about the characteristics of these mean distributions of the sample? In fact, various large-scale experiments and computer simulations that have been conducted by experts have shown that whatever the distribution of the parents' populations is, the mean distribution of the sample is always close to the normal distributions, with the mean that is close to the population mean or mu, and the standard deviations that is close to sigma divided by square root of n. This indicates that there is a mathematical relationship between the population identifiers and the sampling identifiers. In other words, the samples can represent the populations. The theorem that the sample can represent the population has very profound consequences in the use of statistics. Imagine if that relationship did not exist. How can we draw useful conclusions for managing the soybean farming as shown on the slide if the data on the results of our soil sampling do not reflect the behavior of the entire agricultural land at all? I close this segment with words quoted from the book Small is Beautiful, written by Shoemaker in 1973. Please read it, and hopefully it can motivate you to further study in the next module about the inferential statistic. Thank you and goodbye.